All right, we are on to chapter 11. Okay, so we have refrigeration cycles, and just wanted to mention that you should have saw my email that we moved the dates back, basically. So we have chapter 11 today, chapter 11 on Monday, review on Wednesday, and then the exam that Monday. Okay, so exam 2. All right, so then it pushed the different assignments around too there. So we have done chapter 9, which dealt with power cycles with a fluid that was a gas, right? We had a Otto cycle and diesel cycle, which were closed system power cycles, right? So they're heat engines or power cycles, closed system, and then we had the Brayton cycle, which is the gas turbine cycle. So that was an open system that dealt with a gas as a fluid. Okay. Then we have in chapter 10, we dealt with a fluid changing phase, right? So we had that latent energy that we're trying to take advantage of within the Rankine cycle, right? So that was a open system also. Each component was an open system flowing in and out. When we talked about diesel and Otto, those gas ones, it was a closed system. It was the same mass throughout the whole cycle there. Okay, so we had the Rankine cycle and modifications, Brayton cycle modifications. Now we're switching. We still have cycles, but it's a refrigeration cycles. Okay, so now we're trying to cool something, right? Instead of having a heat engine, we have a refrigeration cycle. Okay. All right. So in this one, we're going to be looking at basic concepts of refrigerators and heat pumps. The cycle that we'll be looking at is this ideal vapor compression refrigeration cycle. We're going to compare it and see how it differs to the actual. Okay. Looking at factors involving selecting the right refrigerant, because there's many different types of refrigerant. We have R134A in the back of our book, but there's many others. Okay. The operation of refrigeration and heat pump, how we have to, when we have innovative or different vapor compression refrigeration systems, how do we look at them and analyze them? We won't get to the absorption refrigeration system. It's in your book, but it's not in the slides. And then we'll kind of talk briefly about the gas refrigeration system, so gas flowing through versus R134A, which can change phase. All right, so we'll start with kind of a remembering of chapter 6, right, when we dealt with a refrigerator. Okay, so the refrigeration cycle, and then the heat pump, right? So we're going to be looking at the details inside those circles, right? When we dealt with chapter 6, we had when we operate a refrigeration system, we have our refrigerated space here, right? So that would be our TL, and then all our components kind of in the back of the refrigerator, not in the refrigeration. That's the refrigeration cycle right here, and we're moving this heat right here out of that refrigerated space into here, and then we're dissipating heat on the warm environment, the back of the refrigerator right there. Heat pump, again, we have our cold outdoors in this case, and then we're pulling that heat from the cold outdoors into our cycle, okay? Putting in work, right? We're moving that heat then to a high temperature reservoir. In this case, it's a house, right? So here we had the warm environment TH. Okay, so to move heat from low to high, right, we got to put in our work, right? The Clausius statement from chapter 6 tells us that, okay? All right, so then we have our coefficient of performance. Okay, so we have one for the refrigerator, one for the heat pump, right? Because the desired effect changes. Okay, this is one of the most common mistakes I see is not recognizing whether something's a heat pump or refrigerator and doing the wrong coefficient of performance, okay? So a refrigerator, we're trying to cool something, right? So this Q dot out is our cooling effect, is our desired output. In a heat pump, right, we're trying to heat something, so QH is our heating effect, is our desired output, okay? Yeah, we'll go through the slides today too, and then we'll get to finish one example, or at least get through most of the example. Okay, so in the cycle itself of where the vapor compression refrigeration cycle comes from is, first we start off with that Carnot cycle, okay? And we did this in the heat engine, right? We threw the Carnot cycle and said, okay, can we make this happen? Because that's a reversible cycle. So in the refrigeration, we're reversing it. So we're going counterclockwise, okay? Right, and the refrigeration / heat pump, where we have it going clockwise in a heat engine, right? Through the cycles, it would go clockwise, refrigeration, counterclockwise, because that requires that network in, and the refrigeration heat engine goes clockwise, and that means you get a work net out, right? All right, so we look at this and we see whether we can do this, right? So this constant pressure, constant temperature through the dome, we can do that. We did that in the Rankine cycle, same with 1 to 2. So we can do that, changing phase, have heat transfer. But the big, so we can say we got smiley faces here. We got a smiley face there, right? But the thing that's challenging are these two, right? If we want to go from 4 and drop pressure and temperature down to 1, we would use a turbine, okay, to go isentropically down. But we're doing that with the high water content, right? This is a low quality, so maybe here's 0, which is all saturated liquid, right? And then here, we've only moved that much distance, so maybe it's quality of 10, so it's 10% vapor, 90% liquid. Well, a turbine does not like this two-phase kind of thing going on, and then especially then with all that high amount of water, okay? So that becomes not practical. And then the other one is this 3 to 4, we're going from low to high, so we would have to compress, okay? And we use a compressor here. Again, this is two-phase, okay? We have a high amount of vapor, but still a lot of liquid, and a compressor does not like that also, okay? So both of those processes are frowny faces. Okay, and so we got to change it for those processes to make it work, to get something close to the Carnot cycle, okay? And we see the other part we see is here's the coefficient of performance for Carnot, which is the reversible one on your equation sheet, same with heat pump, right? And the big thing you can kind of generalize and see is as the temperatures get closer, TH and TL, the coefficient of performance gets higher. As the temperatures move further away from each other, the max coefficient of performance, which is the reversible one, the Carnot, gets smaller as you get the temperatures away from each other, okay? So we have that as a limitation. All right, so then we change and we create our ideal vapor compression cycle. So we've modified what we did on the last one. We still have a compressor. Instead of a turbine, we put an expansion valve in, okay? So that's like a throttling valve, okay? We have our heat exchangers on the top and the bottom, okay? So we can walk our way through this, this cycle. We start at 1, okay, saturated liquid. So we make sure it's all in vapor form before we do our compression, okay? So right here, we're compressing. It would be isentropic compression to 2, okay? And then we're high pressure and temperature. So now we have a high pressure and temperature, and we can reject heat to the warm environment. So the temperature of the refrigerant in the condenser is going to be hotter than the warm environment. So we can make heat go from high to low. The warm environment is a lower temperature than what we have here. Okay, so that means we can condense and get to a saturated liquid. So we call that a condenser because we're taking from superheated vapor and we're condensing it all the way to saturated liquid. Okay. And we get to this saturated liquid and we send it through the expansion valve, which is an isenthalpic device, right? Constant enthalpy, so isenthalpic. So where delta H is 0, we go through and we get to 4. We would have been at 4 prime if we had a turbine, okay? But we can't practically. So we go to 4, and now we end up in our evaporator. So the other thing we should say is we drop the pressure in the expansion valve. So by dropping the pressure, right, because this is our pressure 1, pressure 2, here's pressure 4 equal to pressure 1. Oh, this is, sorry, 2 equal to 3. Here's pressure 4 and 1. We drop the pressure, and by dropping the pressure down to here, we drop the temperature significantly, right? We just dropped it by that much. Okay, so we dropped the temperature so much that the temperature here is lower than our refrigerated space. So if we're using in your home household refrigerator, the refrigerant going through the evaporators at a lower temperature than you're trying to utilize and cool, say, your lettuce or something, or in your freezer, say the refrigerant's lower than that, the 0 degrees Celsius you're trying to keep something frozen. Okay, so then you can have heat flow from your refrigerated space into the refrigerant in the evaporator and make it evaporate and go to a saturated vapor. Okay. The other thing that goes along with this vapor compression cycle is these two states. Okay, we have a saturated vapor, quality of 0 or quality of 1 right here, right? And then here we have a quality of 0 right here. So that goes with it. Okay. So now looking at this on an ordinary household refrigerator, we have our condenser, evaporator, and our expansion valves here. Okay, if we look at it, we see the compressor running through. We have our condenser rejecting heat to the your kitchen's air in the back, and that's why you want it some distance away from the wall to try to allow that heat to transfer into your kitchen air. Okay, flows through. And then we have our capillary tube, which is just a very tiny diameter tube. Okay, so that's dropping the pressure, which drops the temperature. Okay, so again, constant enthalpy device. Okay, now we have a very cold, very low pressure, very low temperature refrigerant, and we can now transfer heat into that refrigerant. Okay, so we transfer that heat into that refrigerant and then take it down back to the compressor. Okay. Here we see the coefficient of performance for this device, for the refrigerator and the heat pump. And it's every single device is 1 inlet, 1 outlet, 1 inlet, 1 outlet, 1 inlet, 1 outlet, right? So that means we can just use open system conservation energy on every single device, neglect kinetic and potential, right? And all we have is delta H's when we divide out mass flow rate. So we can, since the mass flow rate is the same all the way through, the mass flow rate cancels. Okay, so we have Q.L, we have 1 minus 4. For work net in, we have 2 minus 1. Okay, heat pump, we're looking at the Q.H part, so it's 2 minus 3. And again, 1 minus 2 for our work. A lot in HVAC, they might use in HVAC industry, they use the pH diagram. So that's where you kind of see the idea of work here is on the x-axis, because you know the work slash heat. So we have our energy delta H's here, and then we have our change in pressure here, right? So it kind of gives us that lowdown of what's going on. With 1 to 2, we're putting in work. 2 to 3, we're rejecting heat. 3 to 4 is our isenthalpic valve, or constant enthalpy, and then 4 to 1, again, that heat that we're adding. All right, so here we have our actual. Okay, so in this case, we've changed it from the ideal and kind of looking at the actual and what's different between those. And the big thing we see here, so let me correct these labels. This is 1, 2, 3, 4. This should be 5, and then this should be 6. Okay, and 7, 8. So you see all these different states, and that's because they're breaking up this pipe section: 2 to 3, 4 to 5, 6 to 7, 8 to 1. Okay, they can have heat transfer going on between those and pressure loss between those of friction, so that you get this change between those states. Okay, because you got to connect those components together, and they might be a long pipe and things happening at those points. The other thing that happens, just like we saw in the other chapters, is we can have fluid friction causing pressure drops, and that's what you see here. There's a pressure drop. Here you see a pressure drop again. Okay. Another thing that we have is the what happens before the compressor, state 1, is superheated. So it's not. So the state 1 is not at a quality of 1. It's in the superheated region, and we do that to make sure, as the system's turning on and off, and variability and operation, that it's never going to be a saturated mixture and in the dome and see some liquid. Okay, so we superheat it just to make sure, just to be sure that the compressor is not going to see that type of fluid. Okay. And then the other thing we do on this side is we actually cool it, subcool it. So take it to the compressed liquid region a little bit, because then when we put it through the expansion valve, or the expansion valve, we end up down here, and so we get this QL that's a distance like this. If we didn't, and we stopped at the dome at 0 quality, we would expand down, and we'd only be somewhere around here. So we end up getting a larger cooling load, this QL, by subcooling it a little bit over there. Okay. All right, so second law analysis, so this is just chapter 8. So you're just doing chapter 8 to each device, each component, or the max COP is just the reversible, or we look at the whole system and put our boundary around the whole system, and then just look at it. So if we were to put our boundary around the whole system, you would just have exergy from QL, exergy from QH, because there's no exergy from work, right? So we could look at the whole system and look at the extra destroyed for the whole system, or we could put our boundary around each individual device and do an exergy analysis to see the X destroyed in each device, and then see what device we need to do better, design better. Okay. All right, selecting the right refrigerant. Okay. Okay, so there's many different refrigerants. Okay. So one of the neat things to even know is that water can even be a refrigerant. Okay. You don't use it in your household refrigerator because you're trying to cool something down to, 0 degrees Celsius. So that's not good for water. It would just freeze as a refrigerant. But if, say, you were cooling something from 200 degrees Celsius to room temperature or something like that, or 100 degrees Celsius to room temperature, you're not going near water's freezing point, so you could use water as a refrigerant. Okay. You just run it through, and you're just using that process that you see in the vapor compression refrigeration cycle. But to get a fluid that works well at the temperatures we want, say in your household refrigerator, there's the link between your pressure and your temperature, right? So if the cycle on the TS diagram looks like something like this, like a general drawing, right? Well, you have right here, you have a pressure, right here's your temperatures, right? When you're going through the dome. Well, you need to transfer heat from a low temperature here, and then here to a high temperature. Well, if you're saying trying to cool from 0 degrees Celsius into that refrigerant, then that refrigerant needs to be at around negative 20 degrees Celsius, a good delta T for heat transfer to go from low to high. So this could be around negative 20 degrees Celsius. So we would need a refrigerant that works well at negative 20 and is linked to this pressure. So that would be the PSAT at negative 20 degrees Celsius, right? And then this one, if you're cooling into the atmospheric air, then the atmospheric air's, around 20 degrees Celsius, let's say, then this here needs to be 40 degrees Celsius. And then there's a PSAT that goes with that, right? There's a saturation pressure at 40 degrees Celsius, okay? Well, so kind of got your temperatures there. We kind of get a rough thing on what our temperatures need to be. And there's a pressure that goes along with it. Well, we don't really want that saturation pressure to be like 10 megapascals, right? Like if it's 10 megapascals, that PSAT at either of those, that's a very high pressure. We would need some very thick tubing to deal with that, and a very high designed thick material for the compressor. Everything's going to be needing to deal with that high pressure, high forces if we have that PSAT at those temperatures. Just like we don't want PSAT to be a vacuum either, right? We don't want it to be a vacuum pressure here. Then we got to worry about vacuum and vacuum leaks, right? So we want good pressure ranges, okay? And that's where refrigerants come in, okay, for those temperatures, okay? So we have then these different refrigerants. Even carbon dioxide can be one, but usually it's a different cycle than you're seeing in this, what I'm already showing. Same with air. We'll see air in later, okay? But ammonia is a common one, and the chlorofluorocarbons, CFCs, okay? So these account for over 90% of the market, R11, R12, R22, R134A, and R502. And you can find properties for these property tables. If you go to like a DuPont's website or something like that, the manufacturers of those refrigerants, they'll post that data. They have to develop that data because they want then companies that make refrigeration systems to use their fluid, right? To use their refrigerant. So then they've tested and experimented and figured out the properties for their refrigerants, okay? And publish those. So then people can utilize that data to use it in their system, okay? Another popular one is ammonia, okay? We have industrial ones, all right? So for heat pumps, air conditioners, commercial. We have our R134A in our book that replaced R12, okay, used in domestic refrigerators and automotive air conditioners. We can R502 blends two others, okay. The other thing that we got to be careful with, especially refrigerant, is the environment. Okay, it can damage the ozone layer. So let's think about your car air conditioner, right? A lot of people get air conditioner leaks, or their air conditioner needs to be fixed, and they need to fill the refrigerant. Well, where did the old refrigerant go? It went into the environment, right? When it's got a leak, it's just going into the environment, right? So now the environment, how is that fluid with the environment? Okay, and some are worse than others. Okay, so you got to be careful with that. All right, heat pumps. So heat pump, the most common, I'm pretty sure most of us, I'm not sure, I doubt anybody has one, but it's possible, but that we all have kind of an air-to-air heat pump system. What that means is you're running air through your HVAC air handler, in your garage maybe, and that's going from refrigerant to air there. And then outside you have, you know, your other heat exchanger when it operates as a condenser evaporator, it's outside, and it has air again as its medium of the outdoors. Okay, so that's your air to air systems. Okay, water source could instead, that outside heat exchanger that you have, right, it could be put in the ground. Okay, and so you run pipes through the ground, and now the ground keeps a much more, once you go a certain distance underground, it keeps a more standard temperature, right? And the one big thing about these heat pumps is their efficiency decreases as temperatures go lower. So your efficiency when it gets really cold for one day in December here, right? The efficiency as it drops and gets that real cold day, your efficiency drops. Okay. You also have issues where it could start icing up because you know the refrigerants at so low temperatures, you're starting to drop water out of the air, ices up your heat exchanger outside, and now it has to do kind of a heating cycle that's built into some of those to defrost cycle to defrost that, so you get a lower overall efficiency then. So if you had instead the pipes in the ground, you'd get a better overall coefficient of performance. It would, you know, you have a better one there. Okay. Well, heat pumps are most used, and we have them all around here in Florida, because they're really good when you have a large cooling load, like our summers, right? Spring, fall kind of thing. And then have a small heating load, so relatively during the heating season, during our short winter, okay? So you don't see these where I grew up north in New York, outside of Buffalo, New York. We had an air conditioner system that was just for the summer, and then we had a heating system, right, that was just for heating. Okay, they weren't being used as the same thing. Okay, it was kind of, other than the air handler part of it, you had two different kind of systems and two costs basically with it to have both. Okay, so we had like a natural gas heater system and then the air conditioner heat system. All right, so what's happening when your air conditioner / heat pump switches modes? Okay, well, we can't move the evaporator and the condenser, those heat exchangers, we can't move their position, right? They're stuck, right? There's a heat exchanger in your air handler in your garage, right? And there's a heat exchanger outside, right? So you got those two heat exchangers. We can't just move them. So instead, we move where the flow is going through what device at what time. And that's what you see here. You have basically this reversing valve that's switching when you go between those modes, okay? So if we go through the heating mode, and then here's basically your air conditioner mode down here. So refrigerator, air conditioner mode, and then you have your heat pump, your heating mode, right? So in this case, we have, you know, state one right here. We go through our compressor, flows, raise the pressure and temperature, and now we go through our air handler and maybe our garage, and that is basically a heat exchanger, where now we are getting our Q.H into our air that now runs through our house, okay? So now we've go through, it's our condenser, we get an end of a saturated liquid, or around there, and then we go through our expansion valve, constant enthalpy, drop its pressure, and drops its temperature significantly, okay? And we have our low temperature, we drop it low enough that now we can pull heat from the cold outdoors, okay? This is the outdoors here, right? So now we can pull heat from the cold outdoors. Okay, so the refrigerant has to be at a lower temperature than the outdoors. So if it's 10 degrees, if it's 0 degrees Celsius outside, that refrigerant needs to be at negative 20 degrees Celsius. Okay. And then you can see how that might ice up the, being a negative 20, how it might start icing up that heat exchanger. Okay. So we have our evaporator, and then it flows back. We get to our saturated vapor, and it flows back to state 1, right? Okay. Here again, we didn't move our house, right? Still there, same location, air handler, same location. We just have our reversing valve switch, okay? And now we have state 1, inlet to our compressor, and now the compressor's going outwards, and it's going to the heat exchanger outside. So now that heat exchanger operates as our condenser. Here's the condenser. Here we have our evaporator. And we'll show the evaporator in a second. So now we have heat going to our outdoors, okay? This is our TH, we had our TL here. And now we condense all the way to a saturated liquid. Okay, this temperature when the refrigerant's going through is hotter than TH. Okay, we get to our saturated liquid, we go through our expansion valves. Okay, so we're state 2, state 3, go through our expansion valve, constant enthalpy. We drop our pressure, drop our temperature significantly. We end up at state 4. Okay, so now we have very low pressure, low temperature, so low enough temperature that we can pull heat from the air in the house. Okay, so through that air handler, it pulls heat into the refrigerant. And then the refrigerant goes back and ends up at the initial, into the compressor. Okay, this is our evaporator now. All right, so just by changing the flow direction, we're changing whether it operates as a heat pump or refrigerator. All right, so that's the ideal and the actual refrigeration cycle, and then talking about heat pumps. Here we're going to talk about some more innovation, okay? And why is this innovation? Well, the simple one I just talked about is good because it's simple, inexpensive, reliable. There's not much maintenance that's really required, okay? But if you're now talking about a large industrial applications, they'll take that extra complexity, that extra initial cost if it saves them money in the long run, right? So they want efficiency, right? Not necessarily simplicity, okay? So efficiency, they want to save money in the long run, okay? Because let's say you have Publix over on the west side where they have all their trucks where that's where they store everything before it gets shipped to all the other Publix nearby. That's their storage facility. So they have a huge refrigeration cycle there, a huge refrigeration system. So their power for that compressor, if they just ran a simple vapor compression refrigeration cycle, would be very large, right? And they would want to reduce that electricity cost. And that would be done with some of these innovative vapor compression refrigeration cycles. So we'll talk about a cascade, which is pretty simple. Okay, the cascade one is a simple one. And then we have multi-stage. We'll talk about multi-purpose with a single compressor. I won't get into the liquefaction of gases, but it's in your book if you want to look at that. The cascade, really, it's just slapping one vapor compression cycle on top of the other. Okay, we just have 2 of them. We have 8 states, but really down here we have a vapor compression cycle, okay? And then up here, we have a vapor compression cycle, okay? And we have a heat exchanger that connects the their condenser and evaporator here, so that this is not any, there's no external heat transfer there. That's from the upper to the lower here. Okay, the external heat transfer is when we have our boundary on the whole cycle is there. There's our QH, there's our QL, okay? All right, so what does that do to performance? Is if we start at state 1, we go through the bottom cycle, we have 2, we go to 3, we go 4 through our valve, and then we go to 1, okay? Now we have the upper one, we'll start at the inlet to this compressor, state 5, again, saturated vapor. All right, so we go to 6, now we go to 7 through the condenser, 8 through our throttling valve or expansion valve, and then 5 through the evaporator section there, okay? So what does this mean to performance? We kind of just look at the areas. Well, if we only did a single stage, so we didn't have these 2, we had it just as 1. Well, first off, if we are in 1 to 1, we would have to go all the way to here to get to that pressure and temperature that we would need through this region for our TH, right, to have heat transfer occur. But instead, we're just going down here. We cut it off here, and then 5 goes here. So that just decreased this area that we would have had to do work, compressor work. Okay. The other change is down here. So if we had a single stage from this high pressure from 7, we would have expanded it through a expansion valve all the way down to here, and our point would have been here. So then our QL would have been here, and we would have needed a much larger mass flow rate to do anything there. But instead, we go all the way from this distance to that distance. So we've now just made our Q dot out. We've increased the refrigeration capacity. Okay. The other thing that's interesting about this is the fluids never touch on the top cycle and then the bottom cycle. So that means you could run a different refrigerant down here. You could say run R134A here, and you could run water up here, let's say. Or you could have a whole bunch of refrigerants, or you could do more, right? You could do, here they're showing 3 or 4 of cascading with the cycles on top of each other and have different refrigerants through them. So in your coefficient of performance, you have your Q dot L still down here. You just have work net in. There's 2 compressors. So you have work here and work here. Okay. And then you got to be careful of the mass flow rates. There's different mass flow rates on the top and the bottom, and you relate them with the heat exchanger, because the heat exchanger has no external heat, no external work, so it's only mass flow rate and enthalpies crossing that boundary. All right, this one's a little trickier, but not too bad. And the main things that are new is this flash chamber we have here. And then the other thing we have here is this is just a mixing chamber. All right, so let's work our way around, right? We have state 1. We go through and we compress, right? So we've compressed to 2. That's a tropically compressed. Now we have our mixing chamber, okay? And our mixing chamber, we have 2 and 3 giving us state 9. So for now, we have 3 coming from that point, and we'll talk about that in a minute. 2 coming from this point, and state 9 has to be in between them, right? We're mixing state 2 and 3, so you have to be somewhere in between them. So we get 9 as our outlet, okay? We isotropically compress again through another compressor to get to that high pressure temperature that we need for TH. And then we go through our condenser, become a saturated liquid right here. And we have our expansion valve, so that drops it down to 6. And then this is where we get our flash chamber, okay? And the flash chamber, you can think about it as just, say we had a really big drum, okay? And we put 6 into it, okay? and there's enough residence time, like where that fluid is sitting in there, that 6 comes in, and it's got a quality, right? There's a quality here, so maybe this is 0.4 in this one, okay? The quality of 6, right? Well, that quality of fluid comes in, and this device, this drum is so big of this flash chamber that it causes the fluids to separate. You know, if you have a quality, that means you have a mixture of saturated vapor and saturated liquid. So it's so big it settles, all the saturated liquid settles at the bottom right here, and then all the vapors at the top. So that means you can take the liquid out of the bottom. So that means everything leaving the bottom is a saturated liquid at 7. And then you take, over here, you can take everything at the top, and that would be state 3. So that would be everything leaving as a vapor, okay? And that's your flash chamber, okay? It separates the liquid and the vapor from state 6. So we can use that quality that we have. So quality, I know it's a long time from chapter 3, but quality, the definition is the mass of the vapor over the total mass of that fluid. Okay, so at state 6, the mass of the vapor, we can just change that to the mass flow rate at 3, because all vapor is leaving at 3. The total would be the mass flow rate at 6, because that's the total what's coming into the flash chamber. And then we can get mass flow rate 7 just by doing conservation energy in our flash chamber. It's just 6 minus 3. Okay, so that means we got the liquid going this way, and we got the vapor going to our mixing chamber. Okay. And then we go down 7, expansion valve, and then we have our evaporator. Okay. So it's doing something similar to what the last one was with the cascading, but we don't have that heat exchanger in the middle, we have a heat pump. So in this case, we have the same fluid going through the whole system. Okay, so we can't use 2 different refrigerants, but we get a better system in the middle section. So this, because it's all direct with the fluid directly, heat exchanger, you have just pipes and a heat transfer across the pipes. You don't get as good of heat transfer characteristics as the flash chamber does. Okay, so you have that kind of trade-off between the 2. Here is a slight modification to the simple refrigeration cycle. We have a compressor, pick it up, and then we have our condenser. And then here we use an expansion valve, and we just go to the temperature that's needed for the refrigerated space for our lettuce, right? And then we have our evaporator in that space. And then we expand it again to a colder, drop the pressure in more, so then it drops even colder, and that would take it down to the temperature that's needed for the freezer, okay? So then your cooling, Q.L is this plus this, the refrigerator plus the freezer. All right. I'll just briefly kind of mention this one, gas refrigeration cycle. All it is a reverse Brayton cycle. So when we're saying reversed, is we're just reversing the direction, right? A regular Brayton cycle that we saw in chapter 9 had these processes going to the right, going clockwise, right? So that gives you a heat engine, where a refrigerator, because it has a net work in, it's going counterclockwise, right? So that gives us 1 to 2, 2 to 3, 3 to 4, 4 to 1, okay? And to do that, that means the compressor's over here, because we're raising pressure and temperature. Then we have a heat exchanger. Turbines on this side now. And we're expanding to low pressure, low temperature, and then we have our heat exchanger. Okay, so we're putting a work net in. Okay, there's work into the compressor. There's work out of the turbine, but the compressor work is higher than the turbine work. Okay, so we have a net work in. Okay, and we're moving heat from low to high. And every single component here is one inlet, one outlet. Okay, so what happens in this one is you do get in these gas refrigeration cycle like this, you get pretty low coefficient of performance. Okay, so you're going to get a better one with a simple vapor compression cycle. But the benefit of them is they're simple and light components. Okay, so when you're really looking for something very light, in this case, aircraft cooling, where weight is more of an issue than whether it's simple, okay, or the coefficient performance, then you can go with this cycle, okay. And it uses air, right? It uses air so you don't have the weight of the refrigerant going through it, right? All right, so that's what we talked about. We had talked about refrigerators and heat pumps, that reverse Carnot, where we use that to help create the ideal vapor compression cycle. And we had the actual with the pressure drop, you know, some heat transfer, a little bit of superheating, subcooling, second law analysis, basically chapter 8. How we select the right refrigerant, the switching valves, and the ground heat pump. And we did a little bit on that gas refrigeration cycle, the reverse brayton, and I talked about those innovative vapor compression cycles. Okay. All right, so let's do an example.